Yeah, thanks so much for Professor Zhang for the introduction, and thanks for everyone for inviting me here. Hi everyone, my name is Ziniu. Today I'm glad to share some of the current research about how we can enhance the reasoning capability of the current language models through the reward-guided search and the self-training. So probably you have seen our recent release of the Grok 2 model that we have already achieved finally SOTA results on LLM's leaderboard, catching up the Gemini and the ChatGPT results. And on various of the reasoning benchmarks, including the MATH, MMLU Pro, and some of the visual language benchmarks, will achieve significant improvements. And one very interesting thing is that it not only is just a cool chatbot, but it can also achieve some of the cool demos. Like here, I ask it to generate in the game of a two-player greedy snake in HTML and JS. I'm not sure whether I can show this demo right now. Yeah, this is like a HTML viewer, and I will just copy paste the code our model generate in a single run, showing in this block here. It will eventually generate a game. This is a game not only like a standard like a greedy snake, but it wishes that when you try to please wait a minute. How can I present? It is a gaming that if it wishes that you will cover the other snake's trajectories. That if the other snake hit your body, then he will lose. This is not only simply just a gaming of a single player optimizing the final reward, but it's more like a two-player debating game. For this, I specifically pick up this demo because this is the first project I have been studying AI in my undergrad, where in PKU there's a competition which is some team competing with each other. And the first AI algorithm I learned in my whole studies is so-called alpha-beta pruning. That algorithm is trying to see, for each step, you will have multiple choices. Say that for the snake, you can turn left, ahead, or right. And for each of the steps, you will take considering all possible other actions that your opponents will take and try to maximizing your reward and minimizing the others and prune out some of the passes that will not be optimal. So definitely this is the algorithms that require some sort of complex reasoning. Suppose that we are currently utilizing our reinforcement learning to train the model for playing this game. What the model will do is similar to what the standard language model did, that just based on the current state, predict what the next action. This is the action that's not considering the full trajectory of a certain of a long a future ahead. Similar with the problem that Professor Liu Yan just presented about the time series problems. And this also lies in the very deep limitation of the existing language model in terms of the reasoning capability. We all know that what the mechanism of this autoregressive language model is to predict a base condition on all the previous input sentence to predict the next token. And when it tries to generate a solution for a certain problem, it will just generate one by one by one. Unlike as a human, if we try to solve in the math problem, we will do something back and forth. If we find out that the first step is incorrect, we will go back and correct it. Also similar for the greedy snake and also for Go game, we will try to roll out the certain tree to find out the more promising paths for solving these problems. This motivates me to think whether there's some way to combine all those kind of the well-studied traditional AI algorithms to go back to improving the neural language models. And before I talking about more of my works in this line, I will give a quick overview of some of background in the recent research about this kind of inference-time search. So at this moment, probably many of us are very familiar with a so-called train of thought, that unlike the very standard language task that we do classification, given the task we just predict the label, or train of thought or this kind of language model reasoning will try to generate a rationale, try to explain like how to solving the problem step by step. But as I said, this has an issue that if a certain step is incorrect, it cannot be go back to revise it. So there's some method to improve it. For example, the self-consistency, which simultaneously generates multiple trajectory and calculates the ones that has the majority outputs. Also, there are some works that try to incorporate the research into this domain. What is the back-end mechanism that make this kind of advanced search even really works? So the issue is the key reason is first of all, language model sampling is not deterministic. Most of the time, when we try to predict the next word's probability, it is not we always picking up the maximum one. We will have a softmax with some temperature. With higher temperature, the more diverse the model will generate a very different response. So surprisingly, for some of a very hard problem, for example, probably you have seen this year's some news about the AIMO, the IMO problem, which is the international mathematical competition. Those problems are at least 3 years ago, we think that is very, very hard, and the AI models is not able to solve. Similarly, there's also some very hard coding problem like AOPS, that if we simply just prompt the GPT for model for this kind of a super hard problem, most of the time you will not get a correct answer. But suppose you set a temperature as a high value and sample it enough time, set it 100 or 1,000 times. Surprisingly, you will find that the model has very, very high chance to, by chance, get a correct solution. This is what we call the pass at k, which is simply just sample k times, see whether at least one of them will have a correct response. So yeah, this actually lies as the foundation of why the advanced search even works. It is because that model already has some of the capability. As long as you give it some chances to explore, there will be some chances that it will give a correct solution. And we just need to guide it, finding that answer. Yeah, so then the key question is, how can we find out that specific answer among the 1,000 solutions? Definitely, we shouldn't simply just assuming that among those 1,000, there is a correct one, so we are satisfied. Because that it is not able to be deployed in the chatbot. We cannot ask the customers to sample it 1,000 times. We need some way to pick it up that a single solution. So the self-consistency that I introduced before is one such method to pick up this solution. And a metric to evaluate how good this kind of the selection method works is what we call the best of n. It is slightly different from the pass-k that we don't really do the later on re-ranking. Right now, suppose we generate, say, 100, k equals to 100. Among these 100 samples, we will try to rank them based on their likelihood to be the correct solution. The self-consistency did is based on the majority voting. Say that among these 100 of the solutions, there are 10 containing a certain answer, there are 8 containing another answer. Then we will believe that the one containing the 10, appearing 10 times will be the most probable solution. As we can see, utilizing self-consistency as a simple metric to pick a solution from a bunch of outputs, we can see simultaneously gain if we sample more times. As we draw more samples, the overall accuracy for a certain task will be improved. So definitely, this is a very intuitive way to do this kind of the best of n improvements. But as machine learning researchers, we are definitely I think we are more familiar with some source of a classifier or a ranker. If self-consistency work, why not we train some source of a ranking-based model to predict what kind of the solution will be most probable? That is actually the reward model. And in terms of these kind of math problems, people will try to classify this kind of reward model into two rough categories. One category is so-called outcome-based reward model, which is we are starting from the question, sample the full trajectory. After it has a final answer, we give them the full solution to predict whether this answer is correct. So we have a probability to see that whether it is correct. And then say that we have 100 solutions, we will get a score to rank them, and then we can pick up the ones that is the best. So here is the plot from the OpenAI's please verify step-by-step paper. This like a plain curve is a self-consistency like a curve. Blue one is best of n over the outcome-based reward. Definitely we can see that ORM is better than the self-consistency, but still both methods will be saturated if we sample 1,000 times. It is likely that the real model is not perfect. It's also possible that just looking at the full trajectory is also not very natural as what we did as a human. As I say, we try to criticize our some undergrad or kids a homework. What we did is not only just looking at the final solution and critique how well it did. A more natural way is that we will read it line by line and giving them some feedbacks whether this step is correct, and if it is correct, what are the parts that you did it wrong, and then you can directly revise it, right? So based on this intuition, people have been starting to develop more fine-grained reward model, and one direction is so-called the process reward. Starting from 2022, end of 2022, both OpenAI and DeepMind have been starting to looking at this direction. And the first step they did is ask human to give in some annotation. Let's say that given this question and we have a full solution, again, we split it into each step. And then we can ask human annotators to see what are the first step that you make the mistake. And then we can train the model to see that among all this a step of reasonings, what is the first step that the model will likely make the mistake. And we're only picking up the ones that every step is correct. So based on this kind of method, the OpenAI paper shows the capability that they can identify some of the mistake steps among their results. And at least their cherry-picked results are very promising. So again, go back to this curve, we can see that this orange curve will monotonically increase, and eventually achieving very high MATH results. Even with 1,000 draw samples, the improvement is still not saturating. However, definitely this PRM is promising in terms of this specific problem. But as I said, the early stage of the researchers in this line will rely on human annotation. But let's think about that, is it the correct way to do it? So math is a certain kind of a problem. But in general, how we utilizing the language model is very, very general and open domain. We cannot ask a human to give this kind of line-by-line step annotations for every kind of a problem. That is so expensive, and we cannot even afford that. That is the intuition that I have been starting to think about. Whether there's an automatic way that we can just utilizing our current policy to generate some traces and automatically find out this kind of per-step annotations. Utilize this to train a better model. Suppose we have a better planning model with this kind of more advanced search. Then, based on this best of n, we are able to generate higher quality reasoning traces than simply just prompting the model once. Then it's very simple. We just distill our current model based on a more advanced policy. That is so-called the self-improvement and those hype about the so-called Q-star or strawberry. All of these fall into this line of a direction about how we can further improving the model. So the key component to making all of this self-improvement works is I summarize it into these 4 columns. First of all, we need a better planner. Best of n is one of these, and probably we need some more advanced research. The second part is the self-generated data, and including both the per-step annotation as well as afterwards how we can collect higher quality reasoning traces. The third part is the capability that our language model as an agent can interact with the full environments, utilizing those tools to improving itself. And eventually, we need the scalable algorithms that can consume all of this kind of data and spending more inference time compute to improve itself. Okay, so finally, I finished the background. I started to introducing some of my works in this direction on both the mathematical problems, some playing the game, and how to utilize this to guide the generating some music. First of all, I will introducing our work collaborated with the very talented students in Tsinghua data mining labs called ReST-MCTS, LLM self-training via process reward guided research. This curve, this figure looks relatively similar to what I introduced before. Starting from the question, we wish to generate a step-by-step solution. But right now, instead of directly generating the k response simultaneously, independently, we are following a tree. Let's say that given the hard question like a coding, we will firstly think about what is this kind of a problem, which algorithm we want to use. Should it be a dynamic decision, like dynamic programming, or we just do brute force? Based on these different decisions, we will starting from one node to expand further. Say that we write the first line of code and then write the second line. Through this tree search generations, suppose we already have this kind of process rule model that we know that at each step we have 5 outward nodes. We know that which certain nodes is more probable. Now we can simply just give higher chances to sample that node to expand our tree. That will give us higher chances to spend less compute to solving the hard problems. Okay, and in this work, the core contribution is not only just this tree search side, but more interestingly, after we collected such reasoning traces, we will utilizing the final feedback to backpropagate it to each intermediate steps, a per step value, and utilize that to further training our process rule model. So as I said, we shouldn't rely on real human annotations to train such model because that is not scalable. An optimal solution is that suppose we have a final outcome step verifier to tell us whether this code is correct. So let's say the final oracle reward is some source of ground truth test cases. Based on this, we can verify whether this code is correct. After we know that some of the code is some of code is correct, some of code is incorrect, and we already know the reasoning traces to generate this different set of the codes. We will utilizing these final outcomes to annotate the per step value of whether this step is correct or no. A very simple intuition is that starting from one node, suppose it has n final traces to generate the final nodes. We can simply just calculate the percentage of the correctness over all these kind of k outputs. Let's say that from one node, there are 90% it leads to the correct answer. It's very likely this should be a good node. On the other hand, if starting from one node, all of the traces it will lead to the incorrect solution. This will be a relatively bad intermediate leaves, intermediate nodes. Based on this, we will train our real model. And also, the final correct traces that we know that is relatively higher quality because it is sampled from our tree search policy. It should be better than simply just randomly sample and lead to the correct answer. And we also can utilizing those traces to further improving our language model. Through this objective, we can further improving both our language model as well as the real model in the self-reinforcement learning loops. Here is a concrete example of how we expanded this tree search over a mathematical problem. Again, that's starting from the problem. The first step will be analyzing it, and then go to the step-by-step solutions. And we will be utilizing the final outcome, say that this is the incorrect answer, and this is also incorrect answer, to backpropagate to all of the intermediate nodes to give it some intermediate value. And those intermediate value will be used to train the real model. Okay, so for the details, you can take a look at the paper about how we do the implementation and some of the mathematical guidance supports. Here, I will briefly show the eventual results. As I said, in this pipeline, we don't need any human annotation of the per step labeling about whether each step is correct. But still, the model can doing some sort of self-improvement. For each iteration, we're just utilizing the final answer to train both the real model and a language model. And this table will show the improvement over the language model itself. A ReST-MCTS over multiple benchmarks, including MATH and the scientific benchmark called GPQA, all gain monotonically increasing, starting from the 0th iteration. And also, we show that our tree search algorithms have much better sample efficiency compared with the existing best of n and best of n with both the ORM and the PRM. So previously, I showed the 3 curve from the OpenOS please verify step-by-step paper. So you just need to know that this orange curve is their best result, and our best curve, this purple curve, is one step above them. In this curve, the x-axis is the computational token, which means that how many tokens you sample from your, for example, OpenAI API, which is directly mapping to how much money you will spend for solving this problem. And the y-axis is after you spend all this kind of money and the tokens, how likely you will solve this problem. So as we can see, within a certain this kind of token or the money budget, our method will have much higher eventual accuracy compared with the existing best-of-n results. We're also showing that our reward model trained via this kind of the per-step annotations will get a much better result compared with some existing SOTA method like MassShift, evaluated by the best-of-n 200. Okay, in summary, in this work, we're showing that spending more inference time compute can enable an existing language model to get higher quality data. So it's not that we have an OpenAI API and we just sample it one time, that's the end of the story. There's definitely much more spaces we can do to improving the way we're solving a specific problem. Tree search is one very promising direction. And the core to make this tree search work is a good reward guidance. But as I said, training a good reward model needs tons of amounts of the data. I think afterwards there will be a good talk by the Turings, and they will expand talking more about how they collected the data and how much expensive they were used. So intermediate way to address this issue will be whether there will be some automatic way, starting from some outcome-based labelings to get some more fine-grained intermediate labels. So in this work, we're showing this kind of the first step to a first trial in this direction, but there's definitely some more further improvement can be done. And for the supervised task with the Oracle answers, ReST-MCTS can help to also collect some per step traces to not only just training the reward model, but also the language model itself. Here is the code. If you're interested, you can take a look and play with. Okay, so let's go back to these 4 columns. The first work I have mainly introducing about the planner side. So this kind of the tree search MCTS not only can help in the math problem, but also can help in some more interesting gaming, such as Avalon. Avalon is a game that I also very likely to play. This is a game that requires 5 players to play with a certain role, and they have multiple phases, including the team selection, voting, as well as the final mission. Among this procedure, the decision is not only a simple, the finite, discrete choices, but also the player needs to communicate with each other to say something to guide his, disguise his own role and try to express some intentions that he wants to be in the team. This requires some certain, much more high-level communication skills, including the deduction, coordination, and deception. Of course, if you just apply existing language model to play in this game, that will be not perfect. It is not as the topest human players. So we have been exploring whether we can utilizing the tree search that I have introduced before to also play in this game. So as in a high level, what we in this specific paper or in the research, the search space is not again per step reasoning, but some of the high-level guidance we wishes the model to satisfy. For example, here, each time we will prompt the model with a specific guidance or what we call the strategy. For example, here the strategy will be: please think about who are the players you suspect are as evil and why. And also, based on this, who is the current round leader and which player are considering to suggest from a team. Blah blah blah. And noted, these are the common strategy human players will be employed. But the key contribution or the interesting part in this paper is that we will not given the model this strategy at the beginning. We wish the model to explore such a strategy by himself. So how to do it? Each time, we will ask it firstly generate and initialize a strategy. And based on this, he can already play the game. And we already know the win rate about how useful utilizing this strategy, he can play a good game. Afterwards, we can ask the model to revise review all of the game trajectory and propose some of the improvement idea. Let's say that right now the language model will say that we can ask again a question asking the reader to identify which player they feel more aligned with in terms of the strategy, something like that. Based on this, we will pick up a certain improvement idea and try to improving our strategy. So this is like we're training a more complicated, like a multiplayer, like a player social deductive game into a specific problem that we can run a search, in which the searching state space is this strategy, and action is the improvement idea. Each time, we will maintain such kind of improvement idea queue and pick up one of the idea that is proven to be useful to improving the strategy and modifying the strategy, like the strategy, expanding the strategy tree. After we have an updated strategy, we'll be plugging into the simulation to get some feedbacks, and so on and so forth. Results showing that utilizing this like a methodology with the game like iterations, our final like AI models like gaming capability will be keeply improving. And comparing with some other existing like a searching-based method, like a greedy search and BFS, this kind of more advanced and organized bi-level tree search will have much more like a sample efficiency to like find out a good strategy in a much smaller like limited of tokens budgets. Okay, so these two works is about the tree search in the language model space. So next part, I will be quickly discuss about work on another direction about the diffusion model, which is slightly different and not slightly different. It's actually have a very fundamentally different about the generation procedure. So the diffusion generation is like it's definitely not an autoregressive generation. It will try to generate the whole like outputs and keep revising it. So it will not have the issue about this kind of the greedy like step taking about the language model autoregressive. But still, we will have in some of the requirements that we wish to satisfy for this specific task. First of all, I will introducing the task we want to solve is to generate the music. Like in our cases, we try to tackle the symbolic piano music, where all of this music is not represented as the time series, but in like more in a discrete spaces about at each time frame, what will be the symbol of the button we want to click for playing the sound. Normally, we will try to train a diffusion model to try to model the overall distribution of the symbolic music datas, and then utilize this to sample new data. The question we want to solve in this specific paper is some sort of condition generation. So, but it is not like a condition generation that we are so familiar with for like text to image, where we can simply just ask for example, GPT, we want to generate an image of dog. For the music, it's much more like nuanced. Many of the music, it cannot be what is the property and what is a certain pianist play a certain music cannot be simply just described via pure language. Instead, those kind of pianists actually build up some theory about what the music should satisfy. For example, some of the chord, some of the paces, so on and so forth. For example, suppose we want to generate A minor music. It is not simply just a very simple classifier, but it needs to satisfy a certain pattern. So this is the task that we wish to solve. And here I show a few of the very more popular chords that the pianist will use to categorizing their music. For example, C minor and D, like a type of music. And each of these kind of the chord is not only just a certain, for example, simply just a volume, but it describes some certain of the pattern about how the sequence of the music play will satisfy. In reality, there is some expertise software, so for example, Music 21, trying to do this classification. And their algorithms to do this kind of chord prediction is very complicated. It requires some sorts of dynamic programming and finding up some time series pattern that our data miner are very familiar with to solve. The key question is, all of these kind of the classifier are non-differentiable. So it's not very easy to be added into the diffusion model. So before introducing our solution, I'll give a very quick overview about our architecture. We will firstly try to encode all of our sequence of the symbolic music tokens as a small image clip. And we're first utilizing a CNN to embed each of the image clip into embedding. and then turn it into a sequence of discrete tokens. Afterwards, we will have a diffusion procedure to try to, starting from a random noise, to eventually output a music. And we wishes that our final music, the x0, satisfy a certain rule, where this rule is mostly represented as a complicated program or the API. What we call API is that, let's say that you have a very complicated software, you throw in an MP3, it will give you that what type of music it belongs to. This is definitely not a neural model, so it's hard to directly calculate gradient to guide the procedure. So how is a traditional way method to solving it? First of all, the general diffusion procedure is starting from random noise, step by step, to doing the denoising and adding the gradient direction to be more probable to the final distributions. And if we the distribution or the direction we wish the model to add into the current data is a so-called score function, which is normally learned from the data. And the whole diffusion procedure can also be represented as an SDE function. So intuition is starting from ST from a very simple distribution, like a random noise, we will statistically climb towards a log P. It's also very similar to what I did describe before about the mathematical reasoning, where that P will become a reward model. So actually, these two line of work is having a very deep connection with each other. Okay, so as I said, eventually we wish to generate a music that satisfies a certain program or the pattern, and this kind of pattern is normally represented as a program. And suppose that we eventually find, given the music as a data, the way we will do it is that this data can be fitted into a program and give you the label. So if we want to adopt a standard way to solving it, most of the time, previous people did, is to train a classifier. What it did about the classifier is that, let's say that we want to do core guidance. Then they will try to collect lots of the data pairs. Like this kind of data will have core A, this data will have core B. And then they try to train the classifier where they can starting from the data X and predict the label Y. And since their classifier is a neural model, they can calculate the gradient to say that if we want to maximize the likelihood it belongs to a certain label Y, what should be the gradient direction to change the X? This is what we call the gradient guidance. So the issue is that for those kind of precise music rules, and many of the cases where we wish our data generation to be precise and controllable, those kind of rules are non-differentiable. And if we want to train a classifier for this kind of a hard, a complicated rule, we need tons of data, and also it's very prone to generalize. So I hope I express our motivation clearly. In that sense, we wish to utilize this rule to directly guide our generation procedure. The way we did it is to model it as the path integral control problems. Due to the time, I will not introducing the mathematical foundation, but in the general, it's similar as I showing at the very beginning. Starting from the initial, the path integral control will model how a certain trajectory will form up a path, and at each specific step, we will calculate the cost. That cost in this rule satisfying problem will be how likely it belongs to that a certain rules. And then we wish to maximizing the joint the integration starting from the beginning to the end for this kind of rule satisfying. However, directly calculating the optimal control is super computationally expensive. So we propose a simplified solution for it. The key idea is that, again, for the diffusion generation, at each step, instead of generating a single output, we will now generate multiple ones. Let's say that we will generate K samples. If you remember the previous curve I drew, in the whole diffusion procedure, only when we generate the final response, all the intermediate step is actually a mix of the random noise with the final patterns. So this X is not able to directly fit into the program. So we're utilizing some existing mechanism called the posterior estimation to map it back from the noisy samples to the most likely final samples for this intermediate estimations. So it can be understood as, suppose the diffusion procedure altogether have 100 steps. At step 10, at step 10, we will draw 5 samples. All of these samples are closer to a noisy sample. We cannot look at its output to know whether it satisfies the rule. But we have another small neural network or small path to try to understand what will be the likelihood outputs of that noisy samples. And then we will feed these noisy, likely samples to our final program to get a calibrated likelihood about if we draw sample 1, what would be the likelihood it eventually satisfies a certain rule. Utilizing this likelihood, we will recalibrate the previous sampling probability to find out what are the paths that among all these 5 samples, which one we should take. In this case, it's not simply just a random generation for multiple ones, but we employ some sort of guidance. But this guidance is not a differentiable or gradient-based guidance, but more like a certain-based guidance. So through this procedure that is very similar to Bing search, among the procedure, we will have some a control to at each step find out the most probable ones that will eventually satisfy the rule. So, but in the experiment, we will show that compared with many of the previous classifier guidance, where this kind of the green ones is the standard classifier guidance, and this final ones is our SGC guidance. We achieve a significantly lower rule satisfying errors compared with training the classifier, even if we collect enough data for that specific domain. But still, the classifier guidance is not that reliable. And as I said, each time we will need to map back the noisy sample to the original X01. There exists some previous mechanism like a DPS or other posterior sampling methodology. Combine these two together, we eventually get the most robust results. So the hybrid approach of our controllable guidance with some posterior estimation will combine the most reliable control. So here I will give you an example of the music we eventually generate. This is our condition. We give it to the model, and this is the output. So this kind of music generation is not only just realistic, but it has much more controllable compared with most of the previous existing musical generation toolkits, because that for all different kinds of fine-grained, nuanced property that you wish the music to satisfy, you can just provide a program or expert software, and we can just plug into this framework to give you some arbitrary guidance. Our collaborator Sergey also have a cool demo that he has a piano. Yeah, due to time, I will not play the full. But in summary, this is a cool demo that he will input his own playing into this model and try to generate a complementary what should I call the complementary music that will help him to get a better overall eventual performance. And this is done in real time, not simply just a cherry pick demo. So as you can see, the model's output, the final generated symbolic music can be sent back to the music piano, and the piano can automatically give him this supplementary performance. which is very cool. In summary, in this work, we're showing the lessons we learned that the precise diffusion guidance can motivate in some new algorithms. And also this kind of very simple Bing searching algorithms has some interesting mathematical guidance, backgrounds about the path legal control that can achieve the final optimal controllability. Here's our code. If you are interested, you can take a look. So in the final part, I will quickly go through several other directions that we can utilize in this kind of the searching and self-improvement, not only just improving the general language, but also some image language tasks. The first is about the self-creation of some visual language preference pair. This lies within these 4 columns about the self-generated preference data set. The key idea is that for some visual language tasks, like solving some VQA, we don't wish the humans to give us some annotation about which one is preferable, but we wish the model itself to generating some preference pairs. The key idea is that we can give in the original image and provide some very detailed step-by-step prompts to generate a good results. On the other hand, we can crop the model or crop the image to make it a blur, such as some of the details is losing, as well as supplementary it with some prompts that encourages the model to include some hallucination. For example, can you think about, for example, here are the back prompts. It said designed to elicit inaccurate description by setting up slightly different tasks, or that you can try to describe an image object that is not inside this image. In this way, we can collect some of the very bad output responses that is very likely to include some hallucination. And then we can add this kind of bad image description together with the existing instruction following data for visual language tasks, and add it into the self-improvement trainings. Through that, we can just take advantage of the existing SFT data to provide augment synthesizing a larger scale of the preference data for visual language pairs. Eventually, this kind of stick method can improve in the final visual language reasoning capability for a large margin. Here we show some example, for this image query, how many gallons of the super meat gasoline I can get with $50. The bad response for vanilla lava will tell you that we are approximately 3.05. But you can see this 0.05 is actually the price per gallon. It's not the eventual thing we want. It definitely is a mismatch about the image perception capability with the instruction following. After our self-curation trainings, our model will eventually get accurate reasoning procedures to get the correct estimation about given the $50, and also the per gallon price, you will eventually get 13.69. So this kind of the ideas can not only apply for simply VQA, but also for any different visual language or multimodal tasks. And lastly, I will show you some my works that are trying to improve utilizing this self-training for some agent tasks on the 3D library learning. So recently, there's also a big news in the Chinese technology, which is the online of the 3D game of Black Risen Wukong. It's a very cool game with very nice picture and the rendering qualities. So we have been thinking about, since we have this current language models, whether we can utilize this language model to help this kind of game design and give us some interesting things and helping even for some eventually build up a more game. At the beginning, I show a very simple a greedy snake. But suppose that after we incorporate it into an agent design, whether it can be automatically generating a Unity game about the greedy snake, that would be very interesting. However, this is definitely not a simple task. If we simply just ask the model, say that we want to generate 3 boxes of different size stacked on each other, and we already tell him what are the assets, the box we want to put, he just needs to give us some location about this 3 box. Typically, for model give me this one. It's definitely not stacking on top of each other. It's just randomly scattered in a line. So it shows that the existing language model actually lacking a lot on the spatial and the semantic relationships, and definitely not fully controllable. On the other hand, what the realistic game developers in RStudio did is that they were utilizing the sophisticated softwares like 3D modeling, texturing, riggering, layout to eventually step by step create a more advanced game. So we wish to build up such an agent to simulate this procedure. In a nutshell, our methods will enable the language model to write the Blender code that can be executed on the Blender software, that they can fetch some of the assets, put it into the Blender, and put each of the asset into the correct places, and give it the image as the output. Since this foundation model have the vision capability, it can take a look at the output image and think about what are the specific semantic relationships that it still fail to satisfy, and keep revising its Blender code. More interestingly, we will try to encourage the model to write this kind of the location placement as some source of high-level functions that satisfying each specific a relationship, such as putting in a hierarchy or putting in a parallel relationships. And for each this relationship function, we eventually summarize them into an external library. So it will be very look like a realistic AI, a game developer. They try to build up a game, and from the experience learned from this game, summarizing a better library such that they can be directly reuse those existing skills for helping to build up the second version of the gaming. Let's give you some example. Like this is a vanilla language model output, which is just a chaotic. It does not necessary to give you a solar system. While this is the output of our model, that he knows that if we want to build up a solar system, it needs to put something in the center and other planets to cycle it. And the cycling part, it needs to, if you look at the code carefully, it will say that starting from a center node, he will put it as a cosine angle, and based on this to calculate the placement of the location. Okay, I will probably not have a time to go over the details of the procedures, but I'm interested to show you that one interesting part of this self-improvement loop, which is our model is able to each time writing the code and feed it into a Blender to directly getting the image output right. Many of the cases, the image output is definitely not perfect. That's to say that even if the model already knows that given this query, it needs to satisfy a certain spatial relationship, the output image is not perfect to satisfy all of them. So we send this image back to the visual critic to encourage it to point out which specific part of this kind of image has some problems. Based on this critic, we will revise the code. And as you can see, for this specific query about building up a town, via this self-critic procedure, it will step by step making the image output more organized. And afterwards, the final perfect code will be summarizing into a library. This part will be done by encouraging the model to see that based on all the existing code you've written, what are the common functions that you can use to put into a library that it can be reused again. So we're showing that after this self-improvement procedure of learn the library, it will generate a much realistic scene compared with some vanilla Blender GPT outputs. And it will also be able to generate the whole city as well as the internal room. And more interestingly, he will utilize this to guide in some video generation. That given the query, will give you a Blender scene as a condition, and utilizing this condition to guide the video generation. So that eventually our whole AIGC pipeline will be much more controllable. It has the Blender engine as the intermediate steps to enable the real users to say that I want to move this person to another place, changing his hair color or changing the uniform or anything. All of these are probably hard to do it in the post-editing step in the diffusion, but much easier done in the 3D space in the Blender because we simply just need to change the texture or anything. Okay, that's all of my past works. As a conclusion, one minute. As a conclusion, I will briefly summarizing what I did right now at XAI. So recently, we have seen that all of these kind of the large language model builders have been focusing on one thing, trying to scale up, which is to squeeze all of the existing human corpus that they can find out, put it into the larger language models, try to train the bigger ones. And based on the scaling law, we can see that the more data, the larger parameters, eventually we will get higher performance. But similar to some scaling law about like the Moore law or other things, it has some limits. The current limit for the language models development is mainly on the data side. Let's suppose that after we curate all the high quality tokens from the human corpus that human already generated, what will be the next step? So at the beginning of this talk, I show this slide that suppose we have a better search policy that given the existing language model, he can already generate the higher version of the output compared with a vanilla generation. Then what about we scale this part up that taking the existing a question human can ask, just guide the language model to generating higher quality outputs compared with his previous version, and put it back into his training loop. Whether this can make the model to do better and synthesizing the next 10 trillion tokens. So likely that 2 or 3 years later, the pre-training of the language model will mainly utilizing the tokens that are not generated by human, but the majority will be generated by language model via this kind of a pipeline. So to make it work, we need some proper guidance to tell you which part is correct. For the standard supervised data set like QA, it's very easy. We can just tracking the answer. For pre-training corpus, it's much more harder because if you just generate the general corpus, it's hard to tell you whether this output is correct. So that's but let's think about that what human did again. In all the history of the Chinese scholars, they're written textbooks due to the budgets of the price of the papers. They need to limit their token. They have the token budget because the paper is so expensive. Yeah. So later on, research scholars of Chinese scholars, they wishes to explain the very ancient sayings. So what they did is that they will try to do the source of annotation. That they try to write this kind of the ancient sentences in some plain languages on the other side. And based on this, maybe a junior students, undergraduate students, or students in ancient China, were much more easier to digest all this kind of the classical textbooks. This can be done also in the language model space. Suppose we given the textual corpus, we find out those kind of the hardest text that the language model is harder to directly model. For example, the archive paper, the textbook, college level physics books. Let's try to turn them into some QA pairs or some of the close amazing tasks. Now we know that there are some certain of the next sentence prediction that is super hard for the model to directly language model to directly predict. So let's ask the model to generate some reasoning traces in between. So there's one PhD student called Eric, who is currently also in our team, in XAS team, proposed a paper called Quiet Star, trying to explore this idea. And we were working as a whole company to trying to pushing forward this direction more and see whether we can combine the search, verifier on the RL and scaling up to the extreme. Thanks for the invitation, and thanks for all the great collaborators. Okay, any questions?